record this. Okay, so let's see if I can do this here. Share content from files. I guess I can't, so I'll have to share from over here. All right, so I have the worksheet key, and we're going to go over questions. Okay, just because you have the answer doesn't necessarily mean you know how to do that. Okay, so all right, so let me see if this works. All right, I'm going to try something different here. Just give me a second. All right, so share the desktop. That's going to work better for me, except for I lost my document. All right, give me a second here. Documents, classes, 2, chapter 1, worksheet, key. There we go. All right, so I'll make that larger here. But the idea isn't just to get the answers, and I'll post these answers on Canvas a little bit later on. But I want to make sure that, you know, not just you know the answers, but you know how to get them. Okay, just see if I can do that. All right, so number 1 says, well, for this first 3, it says identify the parent function. And hopefully you identified it as the square root function. Pretty obvious. And did it move 4 units left? How did you tell that it moved 4 units left? What'd you do? How'd you know it moved 4 left? What'd you do? You add to x, you move left. Could you also have graphed it?
Yes.
Yes. Okay. Yeah. Add to x, move left. Bingo. Graphing it can help too. 2. It's h of x is x minus 4 to the 3rd power. So I can make this bigger for you. I won't say that one. Okay. Well, hopefully you identified it as a cubic parent function. The dead ringer, because it's what? X to the minus 4 cubed. And it should have moved 4 units right. Something's happening directly to x, so it's horizontal. Add to x, move left, so subtracting means we move right. You could also graph it to double check that. Number 3, h of x is 4x squared. I think the parent function was quadratic. Once again, hopefully that's easy because we can look at the rule. It looks like it looks like the quadratic rule because it's x squared. And it's a vertical stretch by 4. Now, did anyone think that was horizontal? Now, here's I'm going to try to write on this. This, oh, I can't write on it. It won't let me write on it. Okay. This 4x squared is a vertical stretch. If it was something horizontal, it would look more like that. That's kind of the question Ben asked yesterday too, right? Does that make sense? Something's happening to, you know, really, it might help us to rewrite this as 4 times x squared. Because then we can see we do the squaring before we multiply, right? So the location is important. So if we got that wrong there, it's not a big deal. We'll just have to make sure the next time we remember that. Okay, so it's actually a vertical stretch by 4. Right? Not too far. Give me a second here. All right, so for these few, graph the data from the table, describe the parent function and the transformation that best describes it. I'm guessing you used Desmos here. Did you? To make a scatter plot? And we're going to do some of that today. Hopefully number 4, you thought it was a cubic function, and I think it actually should be down 1. I put up 1. I screw up 2. I think it actually should be down 1, shouldn't it? So I'm wrong there. Okay, just making sure you're paying attention. Or I screwed up. Okay, I screwed up. Number 5, if you graph that one, I think you would see that it's a square root parent function. And we have a horizontal stretch by 2. Okay. Now that can be tricky to determine that it's a horizontal stretch also. Right? I think the reason that we get a horizontal stretch would be normally at the square root of 2 would be smaller than that. Okay. If you said vertical compression, I get what you're saying too. But if you look at the graphs, right, that's what we should be looking at. Now, 6 and 7, we had some questions on those. I maybe did more work than you did, and that's okay. Okay, compare and contrast. What I did is I kind of just listed things. But if we're comparing, not contrast, just compare the domain and range for the parent function quadratics. Well, and linear functions, do they have the same domain? Yes, and their ranges are quite a bit different. And this should be ranges greater than or equal to 0, another typo on my part, okay? All right, so you can put a check mark in. You grading this one for me, Devin? You're counting, you taking this for a grade for me?
No.
Since I screwed up, good, thank you. Just joking around, okay? You can't tell I'm joking though, right?
No.
Because you can't see my face, all right? All right, so they have the same domain, their ranges are different. Basically, you know, this should be y is greater than or equal to 0. 7, compare the domain and range for the parent square root function and the cubic function. Well, basically square roots, that's where we have restrictions. X has to be greater than or equal to 0, as does y. Whereas cubic functions, it's all real numbers for both, right? So they have quite different domains and ranges. All right. Any questions on that first page? Comparing the two, was the first page easier than the second? Okay. No matter of opinion. All right. Now, for these next few, okay, first thing we had to do, and I think I did number 1, didn't I? Did we do number 1 in class?
Yeah.
All right. So the first thing we had to do was find the equation of that line, and we figured the equation of that line was y equals 2x minus 3. Okay, y equals 2x minus 3. So then if we moved everything 3 units left, and I really wish I could write on here. You know, I can't. I just figured it out. If we're going to move it right 3 or left 3 units, g of x is going to be f of x plus 3. Is that right?
Yeah.
And then if we take we had 2x plus 3. Excuse me, I'm going to backpedal here a second. Eraser. If we find f of x plus 3, that's going to be 2 times x plus 3 minus 3, which simplifies to that. Agreed? I'm going to try to show you as much work as I can. Slow me down if you have a question. If you need something further explained, that's what I'm here for. All right. Number 2, vertical compression by a factor of 1/5. Well, I think the equation here, the y-intercept looks like it's 1, and the slope is down 1 and over 2. So I think our equation there is f of x. Did you get negative 1/2 x plus 1? That's the original. That's not our answer. That's the original. Now, if we perform a vertical compression by 1/5, I think g of x is going to be 1/5 f of x. Whoops. And that's where we end up with that. 1/5 times negative 1/2 is negative 1/10. And 1/5 times 1 is 1/5. All right? Yep.
Is it okay that we answer those in decimals, or should we try to use fractions?
It's okay, decimals are okay. I prefer fractions, but I'm not going to argue it's on right. The problem with decimals is like if it was 1/3, it's not exact, right?
Okay.
It's not 1/3, I know that, but so you have negative 0.1x plus 0.2. Those are precise and exact, that's great. But if we run into something that's not exact, that's where I don't like decimals. Okay. All right. Number 3, we want to reflect that line across the y-axis. Okay. And I think the equation was what? What's the original equation? Negative 3 is the y-intercept, up 3 over 3. So what is it? Was the original function f of x equals what? X minus 3? All right. So g of x, if we reflect across the y-axis, All right, g of x is going to be f of negative x, correct? Which means we're going to replace x with negative x, and that's how we get that. All right, so once again, I think it makes sense to me to write these mapping notations. All right, I think that helps. If it doesn't help you, I get that. You don't have to do everything the way I do it, okay? But I think that tells us how I'm going to make a change to the rule. All right, so any questions on 1 through 3? All right, let me get rid of my writing then. Okay, then we get to number 4. Number 4, we did a problem like this. You can see I made mistakes, so I crossed things off. We want to come up with the linear function defined in the table, and we want to end up with the horizontal stretch by a factor of 2.3. Okay, so the first thing we have to do is find the equation of the, of that line. Well, oops, I went the wrong way, sorry. Well, I look at this, and this is my y-intercept. Oops, I'm gonna go to my pen here. There's my y-intercept. And then what else do I need to find? Slope? What's the slope? Well, I look here, I say up 14 and over 7. What's the slope? 2. So I think our function, f of x is 2x plus 7. Well, now we need to perform that transformation, and it's a horizontal stretch by 2.3. Once again, horizontal stretches are the ones that are a little more difficult. So that means we're going to have f of 1 over 2.3x. That would be our new g of x, which means we're going to replace x with this. All right. Oops. Forgot about the 2. So far, so good. Which means we get 2 over 2.3x plus 7. And I don't like decimals with my fraction, so I turned it to 20 over 23. Is that just moving this decimal over and moving that one over too? Carly, you look confused.
Wait, did you just multiply 2?
Yes, yeah, 2 times 1. Yep, yep. But then this becomes 20 over 23 by just saying, I don't like decimals here. Boom, put it as 0. All right, questions? These are tricky. Like I said, horizontal stretches and compressions, those are kind of the things that takes the longest to wrap our head around. Right, I understand that. All right, number 5, taking the function 1.7x minus 3 and doing a vertical compression by 0.7. I did use decimals because that would end up being what? G of x would be 0.7 times f of x. So is that just going to be 0.7 times 1.7x minus 3? Can you read all that? Is that okay? I mean, I know it gets to be busy here, which leads us to that. Right. So that vertical stretch is a lot easier than the horizontal one, isn't it? They are, okay? They are. Hopefully you're finding that too. So far, so good? Like I said, if you have other questions or need things explained a different way, let me know. I'll try to do that. You want me to do it, recite it in Spanish? Good luck. Kidding, I don't know Spanish. I know one thing in Spanish, a couple things actually. Baños, what's that? Bathroom, yeah. Okay. I've been to Mexico quite a few times, so I know that's what you got asked for. But I know some other things that are not really, not really. If you were actually speaking Spanish, you wouldn't understand. Anyway, so for the next few here, we are taking the function f of x equals x, and we're doing combined transformations. All right? So vertical translation 2 units down, followed by a horizontal compression of 2/5. Well, is that what we end up with by moving it 2 units down? X minus 2? Yes? We're moving the function f of x equals x 2 units down? Well, and then if we perform that vertical compression, that's going to be like f of 1 over 2/5 times x. Well, what's 1 divided by 2/5? 1 times 5 over 2? Yes? So we end up with, if we replace x up here with 5 over 2x, which is just simplifying this, we end up with this piece right here. 5 over 2x minus 2. All right, we're doing one of those at a time. And you can see I screwed up some of these. I went the wrong way. Okay, so I fixed them. Yep.
Why was it x minus 2?
Well, how do you move something down? Okay, to move something down, isn't it going to be f of x minus k? All right. What's our function f of x? It's just x, right? So we go x minus 2. Now, would that also, in theory, be moving it 2 units right? Yes, they're the same thing. But realistically, we're using that f of x, which is x minus 2. Yes, it would also, it's also the same effect as if we moved it right 2 units. I think we talked about that. All right. Number 7, horizontal stretch by a factor of 3.2. Okay. Well, here's the horizontal stretch by a factor of 3.2. I'm gonna jot that up here. I know there's not a lot of space here. F of 1 over 3.2 times x, right? Isn't that how we're going to do that horizontal stretch? Similar to how we did the horizontal stretch in question number 4. Okay. Followed by a horizontal translation 3 units right. All right. This is going to move it 3 units right. Now, did anybody write it like this? If you did, you're not quite right. Well, can anyone tell me the difference between these two? This is moving it 3 units right. What's this doing? You know, Ben? Yes. The difference there, once again, something's happening directly to x here, right? Horizontal, whereas this is happening to our bigger function. So this isn't the one we wanted, but I could see why people might come up with it. All right. All right. Now, number 8, we definitely, definitely want to go over because it's a tricky one. Okay. It says the red cab taxi, excuse me, popping into a mask is a very good idea. Breathing into one early isn't either, but right, the red cab taxi service used to charge $1 for the first 1/5 mile and 75 cents for each additional mile. Okay. The company just raised its rates by a factor of 1.5. So inside here, inside these brackets, is what I have is I have their original price function. Okay. All right. Now, are you guys familiar with point slope form? Maybe not. You are? You ever heard of it? So here's what I did. Is I said basically the first mile costs $1. That's like a point on that line, correct?
Yeah.
The first 1/5 of a mile, excuse me, is $1. Then any miles after that, we subtract that first mile, are 75 cents. All right. Now, if you're confused by that 5x minus 1, think about it this way. X represents the number of miles you've driven. Right? So if I put in 1 for x, that would be 1 mile. I would only be charged 75 cents for those 4 miles above and beyond the first mile, right? So that's where it gets it can get a little tricky. All right? That's where it can get a little tricky. This is a tough question. Now, if the company raises rates by a factor of 1.5, that's a vertical stretch by 1.5, and that accounts for that. Okay, and you can leave it like I have written kind of in red there. I did a little algebra and it looks like that. You don't have to do that. But that is a tough question. All right, that is a tough question. Okay. Now, if you don't like the way I did that one, which is fine, okay, you maybe don't like the way I did that one. What would be another way of coming up with that equation that's in the box here? Anyone think of a way to do that? I can think of another way. That's why I'm going to try to show you. All right, so let's make a table. X is the number of miles. Y is our cost. If we drive 1/5 of a mile, it costs what? $1? If you drive 2/5 of a mile, it's going to cost you $1.75, right? Good with that? 3/5 of a mile would be what? $2.50. Well, what we're doing is we're building a table of a linear function, aren't we?
Yeah.
So, like I said, if you don't like the way I did it, this would work too. From this linear function, I could find the slope. Okay? 250 minus 1 all over 3/5 minus 2/5 over what? 1/5. All right? It might be easier to work with full miles here, but this is basically going to be what? So 150 divided by 1/5 would be the same as 150 times 5. Well, in ours, we ended up with, well, we'll leave it like that for now, okay? We could say that was like our slope. Does that look similar to the slope we have right here?
Yeah.
It's off by a decimal, but is that because we're going x is a whole mile as compared to 1/5 of a mile? Yes. So maybe decimals work better. All right, so then we're at this point. We'd have to find b, correct?
Yes.
Well, I'm going to put in if x is 1/5 of a mile, 1/5, excuse me, and y would be $1. We'd have to find this value. Okay. And I think this would be what's 0.2 times 7.5? I think that's 1.5. B would then be equal to negative 0.5. And once again, that's going to work out a little differently. Here we're using 1/5 of a mile. Here we're using a full mile. Do you see the difference? All right, so it would be a little bit different. All right, it would be a little bit different. Okay. So that's another route to go. Now, another route to go would be if we can come up with this table, it'll be kind of talking about what we're going to discuss today. I'll cancel that. All right, so we're going to move to that. Like I said, I will publish that a little bit later. Okay. So now we're going to move on into let's see, I should have this PowerPoint here. Here we go. We're going to move on to section 4. Now, I'm not going to talk for a half hour like I normally do. We're going to talk for 10, 15 minutes here and talk a little bit about linear regression. Okay, we'll come back to this on Monday and talk more about it. So we're going back to the textbook. Lesson 4 is the end of chapter 1. Okay, lesson 4 is the end of chapter 1. So we're going to fit a scatter plot. We're going to make a scatter plot for data. All right. Today we're going to talk about doing it by hand. Tomorrow we'll talk about, or not tomorrow, but Monday we'll talk about using decimal. Okay. Now the reason we do this, and we're going to do a little bit of regression. Regression is kind of finding the curve of best fit for a data set. We're going to be doing that in every chapter. Okay. So not just chapter 1. We'll be doing it in other chapters too. What happened here? All right, give me a second. Okay. I'm not sure what's going on here. Oh, because I'm at the end of the, I'm in the wrong spot. It's me being, it's my issue. All right. So vocabulary, we're going to talk about regression. We won't talk about that a lot today. A little bit correlation, line of best fit, correlation coefficient. You guys know, you remember line of best fit in Algebra 1? Mrs. Legrand, or whoever your algebra teacher was, probably had you make a scatter plot on a piece of graph paper, then you put a line in there that looked like it was pretty good, right? A trend line. Okay, that's kind of what we're talking about here. Now, researchers such as anthropologists are often interested in how two measurements are related. Okay, regression is the study of how two measurements are related. All right, today we're going to talk about linear regression. Now, if you make a scatter plot, sometimes the data might look fairly linear. Okay, and I think they do here, don't they? They look fairly linear. Now, this is called a positive correlation. Okay, we can also have negative correlation. Negative isn't bad. Negative means the slope would be negative. Does that make sense? All right, so this would have a pretty high positive correlation. This would have some correlation right here. I can't draw on that, so I'm trying. If we got a scatter plot like this, would we say it's linear? No, things are all over the place. There's probably no correlation whatsoever. All right, so correlation measures the strength and the direction of the relationship. Right, the strength and the direction. So this is positive because it's going upward. Okay, this is positive because we're going upward. Now, if there's a strong linear relationship between two variables, we can come up with what's called a line of best fit. We can come up with that line to make predictions about data values that are outside of our table. Right, that's what we're getting at. All right. Now, so we're going to go through an example here, and like I said, I think you've done this before, but doesn't mean that we're experts at it. Albany and Sydney are about the same distance from the equator. Albany must be New York, and Sydney, I would assume Australia. Make a scatter plot with Albany's temperature as the independent variable. Name the type of correlation, then sketch the line of best fit and find its equation. So we're going to do all that stuff. Now, what do you see about the temperatures in Albany and Sydney? Albany's in the northern hemisphere, Sydney's in the southern hemisphere. What's true about the seasons in the northern and southern hemisphere? Are they the same? No. So you can see when it's warm in Sydney, it's cold here. You can also see when it's cold, or when it's warm here in Albany, in the United States, it's colder there. So our seasons are kind of opposite, right? Okay. Now, if we were looking to make the scatter plot there, and it says make Albany's temperature as the independent variable, right? We're supposed to name the type of correlation. Well, here's what that looks like. Albany's temperature compared to Sydney's temperature, right? Now, we could definitely make a scatter plot like that from this data on Desmos, couldn't we? Yeah. Talked about making a table. Okay, so we'll be doing that next week. Maybe we'll do a little bit of that today. We'll see. All right, so here's what it looks like. Now, like I said, in Algebra 1, whenever you took it, some of you took it in 8th grade, some of you took it, in your freshman year. And we would probably try to put a line of best fit in there. We probably just like to go, does that look good? Not perfect, but it looks okay. We try to get the line to balance. Maybe some data values above, some below, but it's not going to be perfect. Now, what could we say about the correlation for that relationship? It's negative. Okay, it's negative. Okay, that would have a negative correlation. Okay, definitely would have a negative correlation. All right. Now, if we were trying to find this line of best fit, we'd have to, pick out a couple points on there, right? All right, looks like one of the points is when Albany is 25. I'm just going to go 25. And then the other one I'm going to say is when Albany is right around 70. It's not exactly 70, but it's close. Okay. So I'm going to go back to the previous slide and see if I can pick those numbers out. Albany 25, was it 25? Oh, actually it was 30. My bad. I didn't look at the scale there very well. It's going to be 30. See that? In between here? That would be 30. My bad. So I think that's actually 31. And then but I did it right on the other one. So I think our first one, let me go back here. Give me a second. Would be 3165. So I'm going to write that 65 right here. And the other one was 75 for Albany. Or actually, it wouldn't have been 70. It's 70. So I'm going to say that would be 46 for Sydney. Okay? So I'm just going back to my table to figure out what those points were, right? Well, now I could find the line of best fit by algebraic means. All right? 46 minus 65. What am I finding? 70 minus 31. What am I finding? Slope. So that would be negative 19 over 39. Now, for the purposes of doing this problem, could I say that's roughly negative 1/2?
Yeah.
Pretty close, right? It's not going to be perfect, but it's roughly, right? If it was negative 20 over 40, that would be negative 1/2. So I'm going to say y, which would be Sydney's temperature, is negative 1/2 x, Albany's temperature, plus b. And then I'd have to try to find b, correct? How do I do that? How do I find that y-intercept? Well, it looks like it's 80, doesn't it?
Yeah.
But should we try to find it more accurately? How do we do that? You know how. Ben.
Point slope.
We're not using point slope. That wouldn't be a bad idea, but I'm going to try to find it a different way. So you're not wrong. I'm just going to go a different route. If I'm using this route, how do I find b? You guys know how to do this. Okay, if I want to find b, I better know an x and a y. Do I know those? Do I just use one of those points? Yes. 46 equals negative 1/2 of what, 70 plus b, which means 46 equals negative 35 plus b. I think that makes b 81. Is that close to what we thought it was going to be? You knew how to do that, right? Just a refresher. Just a refresher. Point slope form would work good though too. I'm not saying that's wrong. So this is our regression line for that data set. Do you remember doing that in Algebra 1? Okay. You probably didn't do it. I mean, you did it on a piece of paper and you had a ruler, right? So it's a little bit different. Okay, a little bit different, but the same, pretty much the same process. Okay. So remember that line. We got negative 1/2 x plus 81. Let's see if they work it out. I'm not sure if they do. All right, they didn't. But anyway, that's how we do things manually. Now, we talked about correlation. Correlation measures the strength and direction of the relationship. Now, remember, correlation can be positive, correlation can be negative. Negative doesn't mean bad. Negative just means what? Negative slope. So a lot of times we assign the correlation, and we'll do that on Monday. It's a value between -1 and +1. Okay? If R, which is called the correlation coefficient, is 1, that means that data set is a perfect line with a positive slope. Perfect line with a positive slope. If the correlation coefficient R is -1, that means it's a perfect line with a negative slope. And R equals 0 means it's all over the place, like this one. All right, so here's some examples. Here it says R is about -0.95, because it's fairly linear, but it'd be negative slope, correct? Here, there's a little bit of a trend, but we're going to get farther away from -1. We're going to get closer to 0. We got -0.6. Same thing here, but this is kind of a positive correlation because as we go this way, it goes up. Okay. So, correlation coefficient is some number between -1 and 1. The closer to 1 and -1, the better the match. The closer to 0, the poorer the matches. That make sense? All right, so that's what that's looking at there. All right. Any questions? Now, we're going to pick up where we left off on Monday and finish up chapter 1. Tuesday will be a little review day, and then we have that quiz coming up on, test coming up on Wednesday. All right, so I'm going to stop recording here.